Here we have a similar situation in which we release an object from rest and it falls through a displacement of 2.3 meters downward, accelerating at 9.8 meters per second squared in the downward direction. And we want to know what the time interval is. The displacement is v naught delta t plus 1/2 a delta t squared. Okay, and we could actually, if we wish, in preparation for what we're going to do when we do projectile problems, which is what we're leading up to, is put y subscripts on the displacement, velocity, and acceleration, just to indicate that this is in the y direction, the up and down direction. Now, the displacement in the y direction is 2.3 meters. Initial velocity is 0. Acceleration is 9.8 meters per second squared, and it's the clock time, or the time interval delta t, that we're trying to find. Ordinarily, to find delta t from this equation, we'd have to solve a quadratic, because we have both delta t and delta t squared in the equation. However, in this case, the initial y velocity is 0, which makes the delta t expression, or term, 0. So that we have just delta sy is 1/2 ay delta t squared. We just omit this term and have this equal to this. Solving for delta t, we easily see that delta t is 2 delta sy over ay, and we plug in the values of delta sy and ay, both of which have the same sign. In this case, we've chosen the downward direction to be positive, and the acceleration and the displacement are both positive. And we get the 2.17 meter per second. Don't think that we're going to measure time in meters per second, and I hope you're more careful than I am about doing your units. Meter over meter per second squared, the meters cancel. Second squared comes into the numerator, and the square root of the second squared gives you the second, not a meter per second. And of course, delta t had better be in seconds. Now, just to see what to do in the case that v naught is not equal to 0, the easier strategy, rather than trying to solve the quadratic equation that we would get here, the easier strategy would be to solve for final velocity, which is either plus or minus the square root of v naught squared plus 2a delta s. And the plus and the minus really depend on which direction you choose as up. When you drop an object, the final velocity is going to be 0, is going to be downward, and if that's negative, then you'll use the negative. If it's positive, you'll use the positive. Okay? Having found final velocity, we can then find the average velocity, v naught plus vf over 2. Multiply that by the delta t to get the delta s, or solve for delta t, where delta t is going to be delta s divided by this average velocity, delta s over average velocity. Again, that's the strategy if the initial velocity is not 0. And we could use the same strategy if the initial velocity is 0. Turns out to be just a little easier to use the strategy we have here. But it really doesn't make a whole lot of difference. Whichever seems to be the better strategy at the time will work just fine.